Good morning everyone. My name is Govindarajan. I am from the Computer Science Department and Supercomputer Education Research Center. First of all, let me thank Manu and Biswa for organizing this workshop and inviting me to be a part of that. I think the idea is great, having these students come together and some of these fine researchers who are in India as well as people who have come from abroad to be able to present some of these newer things that are happening in architecture and talking to you is great. Okay, what I want to do in the next 1 hour or so is talk about memory systems, but I understand that you have had several talks on memory systems, and by now you should at least have a fairly good idea of how memory works, right? However, I will go through some of these details just for the benefit of those who still have some difficulties or doubts about them. Please make sure to interrupt me and ask questions and make this session as interactive as possible. This is, I believe, one of the last but one session or the last session. So it doesn't matter whether we complete all the slides or not. It's more important that you understand at least some of the stuffs from here. And I believe the overall spirit of this workshop is to kind of pass on to you the kind of interest and enthusiasm that the organizers have on computer architecture and computer architecture research to you people. So that's really the idea. So in that spirit, what we will try to do is to ask as many questions as possible, right? And try to see as much as we can understand. It's not important to go through all the slides, okay? You can always download them from somewhere and you can look at them leisurely. That's the whole idea. Okay, so what are we going to do here? So the agenda for today's talk is to give you an introduction to memory systems, then talk about how to understand the performance of memory systems, what is that we have done in this context. Then talk a little bit about stacked DRAM, right, which is coming in the memory hierarchy in some way, and this is going to influence many of the multi-core architecture designs. So let's talk about and understand what these stacked DRAMs are and how to organize them, and talk about their performance also, right? Then of course, using this analytical model, how can we improve the performance of the overall memory system, take a couple of examples and then show you what we have done in that context. That's really the overall flow. Some of the things that I am going to talk about here in terms of the analytical performance model might be somewhat at a higher level because this will involve something relating to queuing theory and other things. I don't know how many of you are familiar with the notion of queuing theory. Not many, but doesn't matter. We will not go into the details of it, but look at it from a higher level perspective, right? And then try to see what it can help us. That's really what we want to come up with. Okay, so let me just start off with the introduction. The question is, of course, why study memory systems? And in the last one day, people would have definitely told you that one of the important issues in memory is the memory wall problem. That is, the performance of the processor is continuing to improve, right? Whereas the memory of the processor is also continuing to improve, but at a slower rate. And the gap between the processor performance and the memory performance is widening. And this problem was referred to as the memory wall problem in the mid-90s, okay? And this problem to a large extent is addressed by means of the memory hierarchy, having multiple levels of caches to address this problem. Okay, so if you want to look at the memory hierarchy in a single processor, typically you have the processor, the L1 caches, instruction and data cache, then you have maybe L2 cache and maybe L3 cache and so on, right? This you are all familiar with. How many of you know what is a memory hierarchy in a multi-core architecture? You must have seen this yesterday, right? Of course, they all know. Asking about the students. Have you people looked at a multi-core memory hierarchy? Okay, so it's not going to be very different. It's something like this. You have multiple cores in a single chip. Each of these cores might have multiple levels of private caches. These caches are local to those cores, correct? And then you will have multiple levels of shared caches, and the sharing could be in different ways. So in this particular diagram, you have one level of private cache, okay, L1 cache is private to the core, and then the L2 cache is shared across all of these processors, all of these cores, right? And beyond the L2 we have a memory controller and then the memory. So today we are primarily going to talk about the performance of memory, and when I say memory I mean DRAM, but one could also talk about other types of memory like PCM and other things, and the model that we have can be extended to those memory as well, but let's focus on DRAM today in my term. Okay, so it's not very different from what you have seen in the earlier slide, except that there are more cores and some of these levels are shared across these cores. That's really what it is, right? No? Yeah, right? So if you are uncomfortable, say so, no problem, right? A no answer, right, is actually a very good answer rather than silence, right? Silence doesn't, we don't know what it is, right? A no means at least, yes, you are not with me. That's good. Okay, so this is really what we are going to see, and the same thing. And okay, so this talks about the latencies of these levels. Okay, typically the L1 cache is in the order of 1 to 2 processor cycles, whereas the L2 cache is in the order of tens of cycles. L2, L3 could be even higher, and then of course you have the memory which is in the order of few hundred cycles, right? And we have the memory controller which basically interfaces with the memory and makes sure that the requests, okay, are sent to memory and the data is fetched from the memory. Did anybody cover about memory controller in yesterday's talk? Yes, we saw things about pre-charge, activation and other things in yesterday's discussion, right? So we are going to see that, and the memory controller is the one which is responsible for coordinating all of those activities. Okay. So this, oh, where did I go? Okay. All right. So the same thing. Now you could see here that I have more number of cores, right, and private L1 caches for each of these cores. And here you have an interesting thing. Here there is a shared cache which is shared across some of these cores. Similarly, a shared cache which is shared across some of these cores, and so on. So each pair of cores share the L2 cache in this particular diagram, right? And of course I have an L3 cache, right, which is shared across all of these cores, right? So another way of organizing these things. So I have all the way down here we have private caches, all the way down here we have a shared cache which is shared across all the cores. In between we have some level of shared cache which is shared across some of the cores but not all of the cores, right? So this shared cache in a sense is private to this set of cores, right, but shared among them, because it's private in the sense that this cache cannot be accessed by these cores. That's what it means, right? So it is shared to certain groups of cores. So you will see this kind of architecture in a multi-core system. Of course you have the memory controller and the off-chip memory. Okay, the same thing drawn in a slightly different diagram, okay, more colorful, right? And you could see that there are these multiple cores, core 0, core 1, core 2 and core 3, and the L1 caches are not shown here, the L2 caches are shown here, okay, and the L3 caches are shown here, the DRAM interface, the memory controller and other things as they would appear in the diagram are shown here, okay. Not much to talk about. We did talk about this memory wall problem which relates to the latency problem, right, the latency gap between the processor speed and the memory speed. Okay, in a multi-core architecture, since let's just look back at this diagram. So what happens here, you have this processor and the different levels of caches on the same chip, and the memory is off chip, right. So any communication or any data that has to be brought in from the memory has to be brought in through this bus, right. So we are going to talk about the issue and problem related to that bus, which is what we call as the bandwidth problem, right. As the number of cores in your multi-core architectures keeps increasing, right, the demand for accessing memory is going to increase, and they all have to be served from that memory bus, the memory controller and memory bus. Today's context, you could have multiple memory controllers, correct? But again, you could still have to satisfy all of your demand through that bus. Okay, as the number of cores increases, this problem is going to become an important problem, and this problem is what is referred to as the bandwidth wall problem, okay, by Solihin and al. Okay, essentially all of this point to the problem that off-chip accesses are expensive from the latency perspective as well as from the bandwidth perspective, right? Okay, again a very quick overview of how the DRAM is organized and how the DRAM is being accessed, right? So this is the kind of DIMM that you would have normally seen in your desktop or laptop, okay, which consists of multiple ranks, okay. So which consists of multiple rank. Each rank consists of multiple devices. These devices together contribute to the word that you are talking about, and within each device you have multiple banks, okay, and each bank itself consists of several rows, and within each row there are several columns, and these columns correspond to the bytes that you want to access from the memory, okay. This is essentially how the memory is organized, okay, and if you want to access some data, then of course you will first identify which rank, and then within that rank which bank, and within that bank which row, and within that row which column you want to access, okay. Again, how many of you have seen this details about DRAM before, in yesterday's talk or before? So all of you have seen this, so you all understand this, right? You all understand this, very good. So if I want to access some piece of data, then after selecting the rank, after selecting the bank, okay, I need to see whether the particular row that I want to access is already available in my sensamp or row buffer. If it is not there, then of course I have to bring that row to my row buffer. So that's the first operation I do, okay, and then after that I will have to access the data that I want to access, which corresponds to the column address that I have. And after I have accessed the data, I have to transfer it through the bus to the memory controller. Of course, in all of these actions, before I bring in a row from the row to the row buffer, whatever row that was previously in the row buffer, I have to pre-charge it back to the memory. That operation also has to be done, and depending on what kind of memory scheduling policy you use, you do the pre-charge either before or afterwards, okay. So that's really what happens in terms of the activities to access a memory, okay. So as I mentioned earlier, activate brings the data, okay, from the DRAM into the row buffer, and read or write, which is basically what we call as column access, reads the data that we want to access from the memory. Pre-charge essentially writes back the data back into the memory, and this is important for DRAMs. Whenever if you are talking about other things like PCM and other things, pre-charge may not be there, but the other two activities would definitely be there. Okay, so why are these things important? Supposing, let's say, we have a simple load request, and if this data that we want to access is not already there in the row buffer, then what happens is that you have to first pre-charge the existing row which is in the row buffer back into the bank, then bring in the new row that you want to access, and then from there read the column that you want to do. So typically this is pre-charge, activate and read, all of them have to be performed, and the latency of this would be as much as the length of this, typically 3 times the latency of a read or something like that, okay, roughly 40 cycles, 30 cycles, whatever that number is, alright. Let's say I want to do a subsequent read from the same row in that bank, right. Then what happens is that since the row is already there, I could actually only do the column access for that, and that would only take roughly 1/3 of the time. as you could see here, right? Another access to a different row in the same bank would mean that I have to again do all of these activities. So essentially what we are trying to say here is that whenever you have a row buffer hit, right, you will only have to do a column access and your access time is lower. But whenever you have a row buffer miss, you have to do all of these activities and your access time is more and the energy that you consume is more. I have forgotten to mention that the row buffer organization that we talked about in the earlier slide, there is one row buffer per bank. Okay? So each bank would actually store its most recently accessed row in the row buffer. So you could potentially have a row buffer hit for bank 1, you could potentially have a row buffer hit for bank 2, bank 3 and so on, and every time you have a row buffer hit in a particular bank, you only incur the column access time, right? And that helps you to reduce the latency. Okay. One other thing that we need to understand in terms of understanding the performance of memory is bank level parallelism. Earlier we said that the device consists of multiple banks, okay, and the way in which the access happens is that many of the activities can be actually done in parallel in different banks, and that's why it's important. So let's look at what is bank level parallelism. Supposing, let's say I want to access, right, a location in a bank A, right. So I give the request, it goes through, let's say, pre-charge, activate and read accesses. Let's say my other request is for a different bank, then except for some initial cycles when the bus would be occupied, as soon as that is over, I can actually start doing my processing in the other bank because that bank is now free, and internally I can actually start moving the data from the rows into the row buffer, and I can do things like that, or I can pre-charge that bank and so on and so forth. So that can happen. I need partly the address bus for some time, the address bus and maybe sometimes the data bus, but other than that, right, the activities that happen in two different banks can be overlapped, can happen in parallel. Therefore, it is important that my accesses go to different banks so that I can overlap them. If they go to the same bank again and again, then all these accesses are going to be serial, one after the other. So bank level parallelism in some sense reduces the latency, and that's why it is important. Okay. Now let's look at one more request to the same bank B2, maybe for a different row, right. Then what happens is that that request has to wait until this request is complete because the bank was busy servicing this request, right. And after this request is complete, this request has to be started. Since this is for a different row, there is going to be a row buffer miss and you are going to do a pre-charge, activate and read access. If in the meantime you get one more request to a third bank, and let's assume that this is a row buffer hit for that particular bank, then of course that request can be taken up before because all of these things can happen in parallel, right. So this essentially says that if you have more bank level parallelism, you can actually perform these operations in parallel. There is still some amount of serialization in terms of accessing the address bus and data bus and doing the transfers through the data bus on a per channel basis. We will not get into those complications here, but this kind of gives you an idea of how this parallelism helps in reducing the access time, right. Any questions so far? Good. Sorry? The two reads cannot overlap, is that what you are trying to say? Yes. Well, actually this is a read within a bank, okay. This basically gets the data from the sensams to an in-between buffer, and from there it gets transferred to the memory controller. So that's okay, right. But yeah, because these are in two different banks. Okay. There are some finer details there which we need to work it out, but other than that, it's fine. Okay. All right. Any other questions? So is this clear? Because what we are going to do as developing an analytical model is essentially try to model all of these things, and then try to see what would be the latency of a memory request. So, the first thing for us is to understand these complications. One is the row buffer hit rate. Why is the row buffer hit rate important? There is a row buffer hit rate, your access time is lower, right? Okay, what determines the row buffer hit rate? Maybe I can ask you that question. Locality of accesses, right? If your accesses keep going to the same row in that bank, right, then it gives you more row buffer locality, right? If you keep going to different rows in the same bank, then your row buffer locality would be lower, right? And row buffer locality is defined for each bank. So, accesses within the bank is what we need to worry about. Okay, sounds good. All right. So, let us just move forward. So, bank level parallelism improves performance. Okay, row buffer hit rate also improves performance. Okay, but of course, there are some minor things like when you want to go switch from one bank to other bank, that you have to leave a few cycles. Okay, those delays are that also needs to be modeled. Okay, we will not get into those details in this talk, but it can be done. Okay, all right. Okay, now in order to use this benefit of row buffer hit, what we can do is that we can actually make our memory controller, right, take some of these memory controller to be smarter and use this in an effective way. So, this particular diagram or the next diagram actually going to explain this in greater detail. The idea is that instead of servicing memory requests in the order in which they come, right, if you can reorder them in some way and make sure that you get more row buffer hit rate, then it would be beneficial, right. Instead of just servicing them in the order in which they have come, that might possibly mean that there is a low row buffer hit rate. But by reordering them within the certain time windows, right, if you can actually improve the row buffer hit rate, then it is beneficial. So, let us see how that could be done. So, one of the memory scheduling algorithm which was proposed way back in 2000 is what is called FR-FCFS, okay, which is one of the earliest memory scheduling algorithm. What it tries to do is that it tries to reorder a request in such a way that it would service requests which would have a row buffer hit within that bank first, and if there is no such request, then it will go to the oldest request in that thing. Okay, I will actually explain this with the help of this example here. Okay, so here we have a set of requests which have come, right, and you could see that we are talking about requests within the same bank. Okay, all these blue requests are for row 0, whereas this red request is for row 1. Let us assume that these requests are waiting. Okay, all of these requests have arrived and they are waiting, and this is the order in which they have arrived. Okay, that is a FIFO order. Now, to satisfy the first request, okay, you will first bring in row 0, okay, and of course, you will access column 1 and column 0 and transfer it to the memory controller. Then of course, the second request in that order is to column 1, that also you could satisfy, right. Okay, before I go, maybe a quick question here, right. So, if I have this, what would be my row buffer, which of these requests would be row buffer hits and which of these requests would be row buffer misses? Let us assume that the first one is a miss, this is a miss. What about this one? This would be a hit. What about this one? Miss. What about this one? Miss. Okay. So, if we have serviced them in this order, we would have seen only one hit and the remaining ones are misses. There is going to be one more thing that will come here, that will probably be a hit. Okay. Now, let us see what happens if I try to do an FRFCS. Okay, I try to service this request, okay, then I try to service the next request, okay. Then in an FRFCS model, since there is one other pending request which is to the same row, which would give me a row buffer hit, I will stall this request and then in an out of order manner process that particular request, okay. And let us say in the meantime one more request also comes, right, then what happens? Oh, animation goes away. Sorry, I think I clicked twice. Let me see. Yeah, okay, right. So this comes, gets satisfied, and of course after that this request comes, gets satisfied, and after all these requests are done, now we have seen, except for the first one, all the 3 requests have been row buffer hits. Okay. Now after this, since there are no other pending requests for row 0, now we have to pre-charge row 0 and then bring in row 1 and access it. Okay, that is really what we do. So this is what is called the FRFCFS model. Yeah, scheduling. Is it for a? Oh, okay. So it is within a rank, right? Within a rank. First you have to decode which rank it is, and then within that which bank it is, and within that it is. Actually these are bits in your addresses, okay, and that basically helps you to identify these things. Okay. Now let us go to the second part of the talk, which is about understanding memory performance. This is in some sense try to give you some glimpse of what could be the type of research work that people would be doing, right. So this is a work where we try to come up with an analytical performance model for memory system. Okay. So we will first talk about memory system design and why memory system design is complex, right. In today's context, when you talk about in the context of multi-core architectures and with the emerging technologies, you could design your memory with DRAM, you could design it with other technologies like PCM, which is a phase change memory, or STT-RAM and so on and so forth, some of which is non-volatile. Okay. These have different latencies and energy characteristics. For example, PCM has a read time which is somewhat comparable to the read time of DRAM, but the write time is significantly larger and the write energies are significantly larger. Okay. So these technologies not only, and of course PCM and STT-RAM do not require a pre-charge to be done, right. So there are certain advantages with that, but you will have to see how the design kind of overall improves the memory performance. And you have a lot of choices also. You can have multiple memory controllers, you can organize your memory in terms of multiple ranks and banks, which bits you choose to select the ranks, banks, the number of channels that you can have, the size of your row buffer and so on and so forth. So there are many parameters that you have to actually decide in terms of designing your memory systems, right. And of course there are these architectural enhancements in terms of memory scheduling, memory channel partitioning and so on and so forth. All these things essentially make the memory system design very complex, because if you choose the wrong parameter or if you choose the wrong kind of architectural enhancement for that particular configuration, then your overall memory performance is going to come down. And the way to kind of evaluate this is that one way is, of course, you could take that particular configuration and for that particular technology that you are using and for, let us say, the memory scheduling algorithm that you are implementing, you could do simulations on a set of benchmarks and then identify whether the performance meets or not, right. And of course, for different configurations you could go ahead and do all of these simulations. That particular model is actually okay, but it would be quite time consuming, because for the different kind of configurations that I have and for the different types of technologies that I want to use and for the different types of architectural enhancements that I want to implement, if I have to evaluate all of them for various workloads, the amount of simulation that I need to do could be very, very large, right. And not only that, even if I spend that kind of a simulation time, I don't get a lot of intuition about what works better and what does not work better, right. I somehow want to know that, roughly tell me how certain parameters affect the memory performance and what should I be doing. Can you give me some feel for that, right. So one way to do is to see whether you could come up with an analytical model where memory performance in terms of, let us say, average memory latency can be expressed as as an equation, as an analytical equation of various things. And if I have that equation in front of me and then say, look, okay, now looking at this equation, I understand that if I change this parameter in this particular way, the performance is going to change that way. Or if I change these parameters like this, the performance goes there, right? The moment I have such an equation, such an analytical equation in front of me, it helps me to do memory system design in a much better way, right? And these analytical models can be actually, this is like analytical expression, right? So they can be evaluated in no time, and you could actually explore hundreds of thousands of even larger numbers of models in less than an hour. And then of course you can find out which one of them works better for you and which one of them may not work for you. Of course, these analytical models are not going to be very precise, okay? They are not going to be accurate enough like your simulators. Simulators themselves have certain amount of errors, but then these analytical models are likely to have even larger errors. But nonetheless, they would give you some kind of a ballpark estimate in terms of saying that these configurations certainly perform much better than those configurations. And of course, you can discard those configurations which are not performing that well and only concentrate on those few configurations which are likely to perform better, do detailed simulations or do detailed architecture evaluations for them and find out which one performs better. So it can actually help you in that sense as a first-hand tool to tell you which of these configurations are likely to perform better, on which you can possibly do detailed simulation. But more importantly, it gives you a handle to find out what parameter affects performance in what way. That is what is the neat thing about this analytical model. Okay? So let me just give you a very quick idea of how to build this analytical model. On the one hand, we have the memory system, right, which we talked about in detail so far. And the performance definitely get affected by the memory configuration you have, the technology that you use, the various design parameters that we talked about and so on. The other thing that affects the performance is your workload, is your program that you are running. If that program has more row buffer hit rate, or if that program exhibits poorer bank level parallelism, etc., the performance has to change accordingly, right? So there are these two components, and we want these two components to be interacting with each other together to tell you what the performance should be. If you consider only one of them, right, then the performance that you are going to predict may not be good enough because it's agnostic of the other aspect, right? If I only concentrate on the memory system characteristics, right, then it ignores the characteristics of the workload, it ignores the characteristics of the underlying program, and therefore it's unlikely to be accurate for all workloads, correct? Because workload specific information is not embedded into the model. So our model is going to embed these two things. For the memory system part of it, we are going to use a queuing model. I'll very briefly talk about this. That essentially captures the organization, the technology that you're going to use, whether it's a DDR3, DDR4, wide IO RAM, whatever it is, the kind of memory scheduling to a certain extent the memory scheduling algorithms as well and so on. The other aspect is the workload characteristics, which relates to things like row buffer hit rate, bank level parallelism, and a couple of other parameters that I will talk about. How intensive is how intensive is the program in terms of memory access? Okay, how often does it access the memory? Is it memory intensive program or is it more of a compute intensive program and things like that? So that aspect is the second component of the memory model, and that is also model, and these two are coupled together in terms of building the complete model, which helps us to predict the performance of memory system. Okay, so how are we going to do this? First, let's talk about the analytical model. So the way that I am going to build my memory model is that I am going to assume that there is an address bus, okay, and then there are multiple banks in the memory, and after the memory is being fetched, the data has to be transferred to the memory controller. So these are the three components that I am going to model, okay. So the address bus is what is initially used to send the address, and I will assume that requests arrive to this address bus server at a rate called lambda, okay. And I am going to model this using what is called an MD1 queue, which essentially says requests arrive in this server, okay, with an inter-arrival time which is exponential, and the service rate of this server is deterministic D, okay, and it has a single server because there is one address bus per channel, okay. So that's really what we are going to model. Again, some of these terms might be very new to you, you may not understand, but don't worry. All this it tries to model is that using this queuing model, if customers keep coming, right, to the server and with an inter-arrival time which is exponentially distributed, and the server takes some deterministic amount of time which is 1 over mu to satisfy these requests, and there is only one server. This queuing model tells you what is the average waiting time for these servers. That's all it tells you. Okay. So there is an underlying theory behind that. We will not have to go into that, but that model helps us to find out what is the queuing delay involved in that. Okay. What is the service time, okay, of this address bus server, right? So that we are going to capture it. Typically, the address bus is used for one cycle if you only want to do a column access. If you want to do pre-charge, row activation and column, then you would use it for 3 cycles, right. So on an average, if you have RBH kind of a hit rate, then for row buffer hit you will require 1 cycle, and for a row buffer miss you will require it for 3 cycles. So that is the average access time, average service time for this request. Okay. Now you could see that my workload characteristics parameter RBH comes into picture here, right. Okay. Now let us look at the next component in my next stage in my queuing model, which is the different banks. Okay. As I mentioned earlier, there are multiple banks in the memory system, and each of these banks can actually service requests independently, right. So they are being modeled as multiple servers, and a request can go to a specific bank depending on which location it wants to access, right. And each of these banks pretty much behaves like an MD1 queue, which essentially means it has a deterministic service time and a single server in that bank, okay, because there can be only one parallel request in a bank. Across bank, of course, you can have multiple requests, right. Okay. We will have to justify this input M, but that we will come to it little later. Now what about the service time within a bank? The service time within a bank is that whenever you have a row buffer hit, you only have the column access time. When you have a row buffer miss, your latency is pre-charge, activate plus column access, right. So that's exactly what we are capturing here. For every row buffer hit, you will have TCL is the access time. For every row buffer miss, you will have column access, pre-charge and row activation, right. So that's on an average what my service time is, right. Okay. Now using queuing theory, we are going to say that if I have a service station which has an MD1 server whose inputs come with an exponential inter-arrival time, right, the output can also be I'm pressing the wrong button. Oops, where did it go? Yes, sir. Yeah. Okay. Let's see. So the output of this server, okay, can also be approximated to an arrival pattern which is whose inter-arrival time is exponential. Okay, that's what the queuing theory says. So we are going to use that and then say that this output of this stage is exponential inter-arrival time, which means that the input arrival rate to all of these servers is also based on that. But of course, these requests going to get split across each one of this, and we have to see how they get split across to each of these banks, and that depends on the workload characteristics, because some workloads may have a higher bank level parallelism, some workloads may have a lower bank level parallelism. Okay. Now we will come to that part of it little later, because if I have some number of requests which are coming here, then they are going to get split across these banks based on the bank level parallelism that is available and things like that. Okay. Now, the last stage in my thing is the data bus server, because after the data has been accessed, after the column has been accessed, you want to transfer it to the memory. So, that requires some amount of time, which basically is proportional to the burst length, okay, multiplied by bus cycle time. Okay, it depends on how much of data you want to send and what is the bus width, based on that the bus thing is decided. And this is also modeled as an MD1 queue, the same thing. Okay. We will not go into any more details of this queuing theory. We will simply say that if I give it, the queuing theory book will tell me what is the average waiting time, right? Because of these servers, right, when a request is being serviced in one of these servers, all other requests which arrive will have to wait, and they will go into the service station only after this request has been satisfied. So, they have a waiting time here, right. So, our idea is to find out how long do they wait here, because that determines the time it takes for it to get through this server. And my overall average memory latency is the time it waits here plus the time to service, the time it waits in one of these banks, the time to get serviced in the bank, plus the time it waits for the address bus, plus the time it gets to service in the address bus. Okay, that's really what it is. But for me to calculate these waiting times, I still need certain parameters which are workload dependent. The service times are already workload dependent in some sense based on RBH parameter, and the amount of requests which are going to be spread across these is also going to be dependent on another parameter called bank level parallelism. Okay. So, let us see how some of these parameters are defined and how they can be defined. So, one of the important parameters is the arrival rate, which is the average rate in which requests come to memory. Okay. This is again a workload dependent characteristics. Okay. We can identify this using what is called the misses per kilo instructions, okay, or kilo cycles, not kilo instructions, kilo cycles from the last level of the cache. Okay. RBH is the row buffer hit rate. I simplified things. We talked about a single configuration RBH can be determined using running the program once, but for each configuration, for each row buffer size and each possible interleaving of things, the row buffer hit rate could be very different, which needs to be kind of measured for those configurations. And the third thing is bank level parallelism, how these requests get spread to these different banks. And the fourth thing which is related to bank level parallelism is the request spread, how the requests go to an idle bank versus how the requests go to a non-idle bank. So, some additional levels of details which are required. So, you want to measure all of these characteristics. One way to do this is that for a particular configuration you can do the simulation and measure this configuration. For another configuration you can do the simulation, measure the configuration, but then you have lost the point, because if I have to do the simulation to measure these things, I might as well do the simulation to find out the performance. So, what I want to do is that I want to measure these values for one representative configuration and possibly use that representative configuration, or possibly use that value for that representative configuration, and then analytically estimate what would be the row buffer hit rate for a different configuration, what would be the bank level parallelism for a different configuration, and so on and so forth. Okay. That is somewhat involved, and I will not go into the details of this, but we have mechanisms of doing this using, for the row buffer hit rate it is using what is called the reuse distance histogram. For estimating the bank level parallelism, it is basically measuring the spread and doing an iterative algorithm and using some combinatorial evaluations. Spread is of course measured for a single configuration and is being used using some level of approximations. Okay. So, these are the things that we kind of analytically evaluate, and as I mentioned earlier, once you have S, you basically spread your request across these multiple banks using this kind of a formula. Okay. Now, let us not go into those details, let us see how we are going to use all of these things together. As I mentioned earlier, what is important is for us to measure or to determine the waiting time, plus the average latency. Right, the average latency will depend on some of these workload parameters like RBH and BLP. So, we have to use that as well and essentially find this for each stage. And the queuing theory tells us that for an MD1 queue, the queuing delay is given by this particular formula over here, where this rho is nothing but lambda by mu. Lambda is the arrival rate, mu is the service rate. Okay. So, that is essentially what is given by queuing theory. So, we are going to use this formula, apply it to each one of these waiting times, and of course, use this for each one of these service rates based on whatever we have calculated earlier, and then write down the total latency, which is basically the sum of all of these things. So, now what I will have is that I can actually have the latency in an analytical form, right, and once I have it in an analytical form, I can actually use it for any configuration that I want. This is what I mean by saying come up with an analytical expression for average memory latency. Okay. Now, we can also do bandwidth computations. I will not go into the details, and using this we can also measure what is called CPI, cycles per instruction. Okay. We do a very crude way of measuring CPI. We say CPI of a particular core is nothing but the CPI of that core when you have an ideal memory which has 0 latency, correct, or all your hits are there in your last level cache, and the average latency for each miss in your last level cache. Okay. So, this part can now be expanded as the latency incurred for your memory multiplied by your cycles multiplied by the number of misses. Then if you add that up, then you will roughly get your CPI. Of course, all of these has certain levels of approximations, and we characterize these levels of approximation, and then what are the reasons for this and whether we could have avoided this, etc., and so on. I will not go into those details. I will also tell you that this particular model can be extended for multiple memory controllers, can be extended for different scheduling algorithms. You can actually model refresh in DRAM and then see what is the impact of refresh in DRAMs and so on. You could use it for a different memory technology like PCM, and of course, you can do what is called a closed network model, which I will not go into the details. So, what we did is that we evaluated this particular memory model by actually doing simulation for all of these configurations and then seeing how the simulation results differ from the analytical results, what would be the error involved in that. We did this for various memory configurations, we did this for various workloads, okay, and we report the performance in detail. I will just quickly show you what is the average error involved in this. So, for each one of these workloads, these are 8 core workloads, we measured what is the difference in the estimated latency using the analytical model and the measured latency from the simulation. Okay. So, you could see that in different workloads, it actually the blue bar is for the latency, the red bar is for the RBH value which is estimated, and the green bar is for the BLP value which is estimated. All of them are estimated because for different configurations we estimate this. Just pay attention to this thing over here, which is the average error. The average error is fairly low. It's surprisingly low that it is less than 5%, okay, for our analytical model, which we found it to be good. More importantly, when you want to look at several configurations and you want to find out which of these configurations are performing better, okay, we found that the best performing configurations in 22 of our workloads, right, kind of happen very well. Similarly, the worst performing configurations kind of match with those of the simulation, right. So, we are able to identify the good ones, the bad ones, and the ones which are in between. And we also found that whenever we ranked some configuration as performing number 4 or number 5, right, in actual simulation it is either +1 or -1, it is not significantly different. So, our model is reasonably able to rank order them in some good way. That is really what I wanted to say from this. Now, I think I am kind of running well behind my schedule. So, what I will do is that I will spend some amount of time talking about stacked DRAMs and the different types of stacked DRAM organization. Okay. I believe this was not covered before, right? DRAM cache was not covered. Okay, that's really what I wanted to do. We can skip details about the DRAM cache performance and the last part of the talk if you don't have time. That's not a problem. Okay, so let's spend the next 10-15 minutes on understanding stacked DRAM and using that as a cache. Okay, so now it is possible, okay, to have DRAM vertically stacked over the processor die, and this is how it looks like. Okay, you have the core, which is the blue part, and then the yellow part is multiple layers of DRAM stacked on the core. Okay, and these are connected by what are called these through silicon vias or TSVs. Okay, so so what we have is that we have a processor, and on top of the processor we also have memory, and all of this come together as a single thing, right? Single package. Okay, now with that what you have is that you solve one of the problems, which is the bandwidth wall problem that we talked about earlier. This of course is not completely memory, because it's not, the size is not as much as what you would want to have in the main memory, but it's reasonably large, much larger than what your L3 caches could be. Okay, so let's see what that is. And what it offers is that it offers very large bandwidth between this DRAM and the processor core, right? And it also gives you this in the same die with a fairly significant level of capacity. So typically we talk about an L3 cache which is in tens of MBs, okay, maybe 20 MB, 30 MB, 40 MB is what we talk about as an L3 cache, right? Whereas you could have a DRAM, stacked DRAM, which is typically in the order of maybe few hundreds of megabytes to maybe even gigabytes. Today we talk about 4 gigabytes of stacked DRAM, 8 gigabytes, 24 gigabytes of stacked DRAM and so on, right? So 2 to 3 orders of magnitude more memory is now available, right, within that processor, okay, and that provides you with a very high bandwidth, actually opens up a lot of possibilities, right? Of course, the access time of this is not, I mean, it's only slightly lower or perhaps the same as the DRAM access time. It's not significantly lower. That's one thing that we need to keep in mind. And this comes in 2 different versions. One is what is called the 3D stacked DRAM, where everything is kind of stacked on top. In this particular organization, the DRAMs are stacked together, the core is on the other side, and there is this silicon interposer which is in between them. It doesn't really matter what organization it is, we are still talking about things being on the same die. Okay. Now, when you have this kind of a memory which is available to you in the same die, you could either use this as a cache, as the last level of cache, or you could use this as a part of memory. It is still only in the order of tens of GB and not hundreds or more. Therefore, it cannot be fully memory for us, right? When I have something like 16 cores in my processor, I can't be talking about a main memory which is actually now stacked, which is only 4 gigabytes or 8 gigabytes. That's not enough, right? So I still have to think of this only as possibly as a part of memory, or I can think of this as a last level cache with a DRAM being my main memory, off-chip DRAM being my main memory. Okay, that is possible, right? So we are going to look at this possibility of using this stacked DRAM as a cache. That's what we are going to discuss. Okay. So how does this change our picture? Again, go back to this previous picture, slightly modified here. We have multiple cores, okay, and each of these cores have some levels of private cache and maybe some levels of shared cache, but they have a last level shared cache, okay, and this is an SRAM cache. Okay, so far whenever we have talked about these L1, L2 caches, they were SRAM caches, static RAM, whereas this stacked RAM that I have talked about is a DRAM. Okay, all right. What is the difference? Static RAM versus dynamic RAM? Anybody knows? Huh? Go ahead. Register technology. Static RAM does not require refresh, right? and whereas dynamic RAM requires refresh. Dynamic RAM is organized differently. Dynamic RAM offers you more capacity, whereas static RAM offers you less capacity, and so on. Okay, what are these differences? Okay, fine. Now, so this is basically what you have as your last level cache, and now you have your stacked DRAM which is available to you. Okay, as I mentioned earlier, you could either use this as a part of the memory and your off-chip memory as the other part, or you could use this as a cache and your off-chip memory as the memory. We are going to talk about this organization of using this as a DRAM cache. Okay. So what are the difficulties in organizing this large caches, right? Large DRAM caches. One is, of course, the size of this cache is very large. Typically, we talk about 1 GB of stacked DRAM, and the question would be like, what would be my cache granularity? Should I use granularities which is of cache line size, typically 64 bytes or 128 bytes, or should I use granularities which are larger, right, similar to the page size that you have talked about in operating system, like 2 kilobytes or 4 kilobytes or 8 kilobytes, right? What should be the cache block size in my DRAM cache? That's one question, right? Depending on that, you have a number of issues that come up. If your granularity is small, of course, you don't waste space, because whatever you bring in to your DRAM cache, you are likely to use it, right? But if your granularity is small, then the amount of metadata that you have to store is significantly large, because for each one of these blocks, you have to have the metadata. And that metadata is going to be extremely expensive because your DRAM cache size is very, very large. Okay? So, even for a cache of 100 MB size, you would require the metadata, which is about tags and other related details, which go into the order of tens of megabytes, which you can't store it as an SRAM, because if you store it as an SRAM, your cost goes up. Okay? So, that is one of the problems. So, where do you store your metadata? Your metadata, if it has to be a part of SRAM, it cannot be this level, and that essentially prevents you to have fine-grained granularity cache blocks in DRAM. Okay? But if you have a larger grain granularity, of course, your metadata overhead comes down, but you may be bringing in more data from main memory into your DRAM cache, and not all of it would be used because you may not have that much of spatial locality. So, you will again lose performance because of that. Okay? So, as I mentioned earlier, there are two possibilities. One is to hold this metadata either in SRAM, okay, or hold the metadata also into your stacked DRAM. Both possibilities are there. If you hold it on your SRAM, then you have to make sure that the size of this metadata is not very large, because if you say that I am going to host let us say a 40 MB of metadata, then there is something wrong, because your last level cache itself is 40 MB, and you have another 40 MB of SRAM just to store the stacks for the next level cache. Maybe you could have actually had an 80 megabyte of last level cache and not had the stacked DRAM at all, right? So, those kinds of things need to be looked into. Other option is, of course, you can hold it in DRAM, but then that gets into other complications, because for every DRAM cache access now, you first have to access the tag and then you have to access the data, which increases your latency. I will show this details in one of the next slides. Okay, I will come back, maybe this we will skip. Let us look at different types of cache organizations for the last level cache, DRAM cache. Okay. So, let us again look at one row in my DRAM. Typically, this could be 2048 bytes or 4K bytes and so on. Now, if I assume that my cache block size is 64 bytes, right, then within this 2K, I could have 16 different cache lines, correct? 16 into 64, right? Did I get it correct? Sorry, 32. I could have 32 of these. I could have 32 blocks within a buffer, within a row buffer, or within a row. Okay. So, in this particular case, let us first assume an organization in which I store all my tag in SRAM. Okay. So, as soon as I have an address, I can send this address to my metadata place, find out whether this, okay, so I will probably have, depending on my cache organization, I will actually go to the set index, find out all the tags, do a tag match, identify which location it is available, get the address, and then use that address to index into my DRAM cache and then get the data. Again, to index into this DRAM cache, it means that once I give the address, this row has to be activated, brought into the row buffer, and then that particular column has to be accessed because it's a DRAM. Okay, all of those things have to be done. Remember that. Okay. So in this very simple organization, I basically have my cache block size as 64 bytes. I could put as many as 32 cache blocks in a row, and let us say if my set has a 32-way associativity, then within that within a single row I could have all the ways of that particular block being stored here, correct? So, and this is only data. The metadata for this, that is the tag for each one of these blocks, okay, is stored in this SRAM tag store. So the way to access this DRAM cache is that whenever I have a miss in my last level cache, I take the address, I give it to this metadata store, okay, it will go to that specific set index, and within that set index it will actually take the tag for all the 32 ways, do the tag comparison, and then tell me that this particular tag or this particular way is the one which is matching, and then what I do is that I use that address and then access my DRAM to access the data. Okay, so this is the simplest way that I can do, and of course if I access it, if I organize it like a 64-byte cache line, this tag storage is going to become very huge. Okay, here is an alternative organization which was proposed, okay, by Lowe and Hill, and here what happens is that I move this tag storage from SRAM to DRAM, and I do an intelligent thing by saying that all the tags which pertain to these this set, all the ways of this set are stored along with that in the same row. The reason I do that is that once I move my tags to DRAM, the first thing that I have to do is that I have to use the address to first access these tags, and after accessing these tags I have to do a tag match, and after I do the tag match is going to tell me where the data is, and then I have to access the data, correct? Now if the tags are not in the same row but they are in a different row, then of course even if I find that there is a tag match, if I want to access that particular location because it is in a different row in the same bank, I am going to have a row buffer miss. I want to avoid that. So this particular organization puts the tags and the metadata and the data for a set within the same row in the DRAM, okay, and to accommodate that what it has done is that it basically lost 3 of those 32 ways, and in those 3 ways it has basically stored the tag, okay. So this is one particular organization. Yet another organization is what is called this alloy cache, which instead of putting the tag separately and the data, the tags, the metadata and the data are in the same row, but the tags are initially together and the data is separately over there. What this does is that this basically combines the tag part and the data part together as an alloy. So you can see that you have the tag which is an 8-byte entity and data which is a 64-byte entity, and multiple such those things are put together within a single row. And this particular cache, alloy cache, is also a direct mapped cache, unlike this cache which is a set associative cache, okay. The reason for organizing this as alloy cache is that in a single access, if the data is available in the DRAM cache, I want to access it. That's the reason, okay. If you have a set associative cache, first thing is that you have to find out, you have to fetch the tag, you have to do a tag match and then find out the way in which the data is available and then access it. right? Whereas if it is a direct map to cache, there is only one place where it can be, if at all it is in the cache, and therefore you can access it. The idea here is to make sure that you reduce the hit latency. That's the reason. Okay, maybe at the expense of increasing the number of misses. So this is the third organization, which is called the alloy cache organization. Vijay's group, Arpit comes from Vijay's group, they have proposed a cache called AT cache. There is another cache called footprint cache, and so on and so forth. We have proposed a cache called bimodal cache, which is a DRAM cache. I will not go into all of these details, but now I will tell you how these caches work. So essentially what we have is that, as I mentioned earlier, you could have the metadata in your SRAM, and if you want to have data in your SRAM, you want to organize your cache blocks as large blocks so that the SRAM size that you require is minimized or is reduced. So in that case, what happens is that whenever you have an L2 miss, you go index into your metadata, identify the address where the data could be available or would be available, then access it from the DRAM cache. If the data is not available in your DRAM cache, then of course go through the memory controller and go to off-chip memory. Okay, so this is the organization with metadata in SRAM. If you want to store the metadata in DRAM, like what happens in the case of an alloy cache or what happens in the case of a low hill cache, then what you do is that whenever you have an L2 miss, right, you could directly go to the DRAM, try to access the metadata, and if it is a set associative cache, do a tag match, identify the location where the data is going to be available and then access it. Or if it is an alloy cache, go to that location, get the tag and data, do a tag match. If it matches, you got the data. If it doesn't, you have a miss and you go to the alternate memory. Okay, that's what could be done. All of these organizations can be improved by some kind of what is called tag prediction hardware, which tries to do this prediction and tries to avoid accessing the tag first in the DRAM and then subsequently making a data access. This tag prediction tries to tell you if there is a hit. It actually tells you where the data would be available in the DRAM cache. So one could do those kinds of optimizations as well. Okay. So quickly let's compare how these things work. Maybe we will stop with this particular slide and then probably take on to some questions and skip the remaining part of the slides. So what you could do is that in the case of an alloy cache, as I mentioned earlier, right, your access comes to the alloy cache, assuming that it is going to cause a row buffer miss. You do a pre-charge activate and a column access, and then get the data, transfer the data, and then do a tag check. If the tag check matches, then you have got the data already, because this transfer is for both the tag and the data together, because it's an alloy entity which is 64 plus 8 bytes all put together, right, and you have transferred all of them together and you are going to see if the tag matches. So if you have a hit, you have the data already. So that's where alloy cache scores well. In the case of a low hill cache, which had the first three blocks storing all the tags, what happens is that after you do a activate, you basically get the tag, okay, you access the tag, you transfer the tag to the memory controller, and you do a tag check, right, and whichever tag that matches, you identify the address, and because it is in the same row, you do a column access and of course transfer the data. So in the case of a low hill cache, which provides you higher levels of associativity, because you need to do a tag check, you first have to access all the tags and then do a tag check and then access the data, right. So this serializes the things and therefore you incur certain penalties. In the case of footprint cache, which is actually a large block cache, where the metadata is stored in SRAM, you basically access the metadata first, do a tag check, identify the address, and of course access the data. Okay. AT cache, which is from the Edinburgh's group, okay, essentially stores the tag in the DRAM, but has a small cache, which is for the tags, which is called a tag cache, okay, and it can actually access the tag cache, and if there is a hit in the tag cache, it will actually do a tag check there, and then from there it will try to do an access. But if the tag is not there in your SRAM, then of course you have to access all your tags first, and then of course get the address and then access it. So these are different ways in which the DRAM cache works. Okay. Essentially what we have done is that we have modeled the DRAM cache also using our analytical model, and we could actually put the DRAM cache, the off-chip memory, everything in our analytical model, and we can get a closed form expression for its performance. Okay. I think I'll probably stop here, and if you have any questions, take. Otherwise we can talk about some of these things offline. How we use this analytical model to design other things is something that I wanted to talk about, but I think in the interest of time I'll stop here and maybe take some questions.